Okay, so 7.4 is adding and subtracting of rational expressions. And you may think that looks really familiar because 7.3 was adding and subtracting of rational expressions and finding least common denominators. So 7.3 and 7.4 really are kind of two sides of the same coin. In that what we did in 7.3 was we did do some adding and subtracting of rational expressions, but only when they had common denominators. And then we spent the rest of the class finding common denominators. So really we were doing the steps necessary for actually tackling the problems that we're going to see today. Because today we are going to add and subtract rational expressions when they don't have a common denominator, which means we have to utilize the information we learned in 7.3 in order to find those common denominators. But then we're going to go ahead and actually do the simplifying. We only simplified the numerical one last time with the unlike denominators. The rest of them we just found the common denominators. Today we're going to do it all. So there's no additional or new notes for today because really we're just expounding upon the information that we learned in 7.3. So we're going to do 6 problems, I believe. We may throw in some extras there at the end. We'll just see what time allots. So we have 2 rational expressions. We have x over 3 plus 2 over x. So the first thing we're going to have to do is figure out a common denominator. And let me give you a hint. If you have a numerical denominator and then a exponent denominator, most of the time you just multiply them together and that's going to give you your common denominator. And so our least common denominator for 3 and x would end up being 3x, which means I need both of my denominators to look like 3x. So if I'm looking at this first rational expression, what is the denominator missing? It's missing the x. So that means I have to take the top and the bottom of this rational expression times x. Because remember, as we saw in 7.3, we have to multiply the top and the bottom because then we're multiplying in essence by 1. It's not that we're adding anything to our equation. We're taking our pizza slice and we're making it into smaller slices is what we're going to do. And then over here for the 2 over x, what is that denominator missing if I'm trying to get to 3x? The 3. So I'm going to multiply the top and the bottom by 3. Remember, when you multiply fractions, you multiply straight across the top, so you'll end up with x squared over 3x plus 2 times 3 is 6 over 3x. Once they have a common denominator, then you can add straight across the top or subtract depending on what your problem is stating. Questions? Clarification? All right, let's do one that's a little bit harder. (4x squared y) plus 3 over xy to the third. So in our denominators, we still have a monomial, meaning we only have one term. But it's obviously a little bit more complicated because we don't just have a single number or a single variable. We have a number in both of our denominators and 2 different variables at play. So if you remember from 7.3, what we're going to do is we're going to look at our numbers first, and we kind of do like a little mini factor tree with those to figure out if they have anything in common so that we can figure out what the least common denominator will be for this problem. We only do the factor tree really with our numbers. So 4 factors into 2 and 2, 14 factors into 2 and 7. And remember, after that, we look for what they have in common. They have a 2 in common, so I'm going to write that 2 down 1 time. Whatever they have in common, you write down once. And then you write down everything they didn't have in common. The 4 had an additional 2. The 14 had a 7. Then we look to our variables. We have two different variables at play. We have an x variable and a y variable. So I know I'm going to have an x and I know I'm going to have a y. But notice that our first expression has an x squared. Our second one only has an x. So when it comes to the least common denominator, we always choose the one with the higher exponent. So over here with my least common denominator, I'm going to say x squared because we go with the highest one. And we do the same thing with our y's. We have a single y on the left. We have a y to the third on the right. So I'm going to choose the one with the highest power, which is y to the third. 2 times 2 times 7 is 28. X squared y to the third. This is our least common denominator. This is what we need to make both of our denominators equal to in order to then do our addition that it is asking us to do. So finding the least common denominator is a little bit more complicated simply because we have more to deal with in our denominators. But the process is going to work exactly like what we did up here. We're going to look at our individual rational expressions and we're going to say, okay, how do I make that denominator, the 4x squared y, into 28x squared y to the third? That's what I need to figure out. So let's look at the number part first. How do I turn 4 into 28? What do I multiply it by? 7. So I'll put a 7 on top, 7 on bottom. Then I look at my x's. I need an x squared. I already have an x squared, so I don't have to worry about that. And then I look at my y's. I have a single y, but I need y to the third. So what do I multiply y by to get to y to the third? Y squared. That's exactly right. So I'm going to multiply this first rational expression by 7y squared, and that will end up giving me the denominator that I'm looking for. Then I look to my next one, which is 3 over 14xy to the third, and I do the exact same process. Say, okay, what do I multiply 14 by to get me to 28? 2. And then I look and I need to get an x squared in the denominator, but I only have an x. So what do I need to multiply x by to get to x squared? X. And then the y to the third's already there. So now I'm set up. This will give me 7y squared over the 28x squared y to the third. Plus, now this is 3 times 2x, which will give me 6x over the 28x squared y to the third. Now I can do my addition straight across the top. 7y squared plus 6x over the 28x squared y to the third. Your problem is also correct if you write 6x first, and if you do 6x plus the 7y squared. That's because we have the commutative property of addition, so it doesn't matter the order that we write it in. Any questions or clarifications on this one before we start doing binomials in bottom? Yes?
So is our answer only what's boxed, or is it also the LCD?
Nope. It's only what's boxed. If they ask you for what the LCD is, then you'll give them that as well. But most of these problems, actually I can tell you if any of them ask for that because I went ahead and did all of them. All of the problems for 7.4 are actually simplifying and getting to the boxed answer. 7.3 had a handful where we just stated the LCD. Good question. Other questions or clarifications? Okay, let's start doing binomials on bottom. I think finding the least common denominator with binomials is actually a little bit easier. Because when we have a binomial in our denominator, we're not going to do any type of factor tree. all we're really going to do to find the LCD is take our two denominators and multiply them by themselves. And before you think, ugh, that's a lot of foiling, that's kind of gross, Pearson actually wants you to leave it in factored form, which means they want you to leave it like this. They don't want you to go ahead and FOIL it to get to W squared, blah, 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 blah. And so you actually don't have to do nearly as much math work as you think you're going to have to do. So when they say to leave it in factored form, this is what they mean. We're not going to FOIL. So then when I'm looking at my rational expression, my first one, and I look at that denominator of W minus 7, well, what's it missing? If my LCD is going to be the two denominators multiplied together, which is W minus 7 times W minus 4, if I have W minus 7, then what am I missing? Yeah, that W minus 4. I just multiply the top and the bottom by the W minus 4. Now, on top, I will let you know, in your numerator, they do expect you to go ahead and do the multiplication, do the FOILing or the distributing and that kind of stuff. But they're allowing you to leave your denominators already in the factored form. So then we have a minus 6 over W minus 4. So the 6 over W minus 4 is missing what? Yeah, the W minus 7. So now in my denominators, I'm not going to FOIL. I'm going to leave those factored apart. But in the tops, I am going to use my distributive property to distribute that W into the W minus 4 and to distribute the 6 into the W minus 7. And I'm actually going to distribute the negative with it so that I can just have a positive in there and I don't have to worry about having a subtraction problem any longer. So I'm going to distribute my W. So I have W squared minus 4W. Then I'm going to distribute the negative 6, which will give me a negative 6W, and distribute the negative 6 to the negative 7, giving me a positive 42. And all of that goes over W minus 7, W minus 4. Well, I have some like terms in here, so I'm not done. W squared minus 10W plus 42 all over W minus 7, W minus 4. Close that. And at that point, you're done. That top's not going to factor into a W minus 4 or a W minus 7 or anything like that to where it's going to cancel. So we don't have to worry about doing that. Trying to see, do we have to do that? Yeah, one of our problems we will do that. But this one we don't have to worry about it. Nope. You can try. I'm trying to think of factors of 42. That would be 1 and 42, 2 and 21, 3 and 14. But none of those are going to factor nicely to give us that minus 10 in the middle. 7 and 6, that's the other one. But 7 and 6 aren't going to give us the negative 10 in the middle. So it's not factorable. It's a prime polynomial on top. So you can definitely try. We will see one here in a minute where stuff will cancel out. And so that is obviously the next step that we want to work on. But other questions? All right, let me get a new page. Where are we at? Where am I at? Up there. Okay. D will be A minus 9 for 3A minus 4. And do be careful, whatever variable they give you is the variable you have to use. I know there was at least one time that I was typing my own answer in, and like I started with the variable they gave me, and then I ended up using X somewhere in the middle of it. Obviously, it counted me wrong because I had multiple variables going on, and I caught it before my third attempt, but... There are a couple of ones in your homework that are very similar to this problem. This problem has kind of a trick to it, which is why I put it in the notes so that I can talk through the trick. If we look at the denominators, what do you notice about them? Or do you notice anything about the denominators? Yeah, if you flip them around, they're pretty much the same thing, right? Like here, it would be a negative 3a plus 4, like if I just switched my order of my denominator around. And here I have a positive 3a minus 4. They're very, very close. Actually, they're so close that if I pulled out a negative 1, then I would have the same denominator. Do we see this? So what that means is I can just pull out that negative and multiply it to the negative right here, and then I actually have the same denominator, and I don't have to change anything else, which is really nice. So I can have an a minus 9 over 3a minus 4. If I factor out that negative 1 and I multiply it by the negative here, that gives me a plus 2a minus 5 all over the 3a minus 4. Just by factoring out that negative 1, I was able to do that. Sometimes when you factor it out, maybe it's easier for you to think about multiplying the other one by a negative and then doing the math. That also works. But the trick is to notice that these are actually pretty much the same denominator. The signs are just different. And if the signs are just different, then we can pull out a negative to make the denominators the same. Go for it.
Like with it being subtraction.
Mm-hmm.
When you change the sign, will that work as well in this case? Because I know you can't do it like if it's an addition problem.
If it was an addition problem and this was a negative that we pulled out, then we could take a plus times a minus, which would give us a minus, and it would turn it into a subtraction problem. So you can still do it the exact same way.
Okay.
With the denominators the same, I'm adding across the top. So I have an a plus 2a, which is 3a, minus 9 minus 5 gives me a minus 14, all over 3a minus 4. Which ones are like that on your homework? I know I saw some. Yeah, number 3 is like that. Number 3 is like that. And I think there's some later on in later sections that are like that as well. Questions before we get into trinomial denominators? All right, let's try a trinomial. I'm going to write the denominator first just because I like to center my numerator. Chapter 7 follows Chapter 6 for a purpose. You'll learn how to do all the different factoring in Chapter 6. That way, when we get to these rational expressions in Chapter 7, we have all the tools available to us in order to factor these denominators and figure out what the least common denominator is. So the very first thing you're going to do is you're going to factor both of these denominators. This first one's the easiest one because I have an x squared as my first term, meaning I have an x and an x. Both my signs are positive inside of my trinomial, which means both of my signs in my factored binomials are also positive. Then I need factors of 6, which is 1 and 6 or 2 and 3. I need factors of 6 that are going to add together to give me 5. Well, if I add 1 and 6 together, I get 7, so it's not going to be that. If I add 2 and 3 together, I do get 5. The order does not matter. If you put x plus 3 first and then x plus 2, it's still the same thing. So that one is factored. Now I'm going to move over to the other one. The other one is a little bit trickier because our a in this case is a 3. But luckily 3 only has one set of factors. It's 3 and 1. So I know I'm going to have a 3x and an x. Now the problem comes in with the next bit. The sign in front of my c is negative, which means I'll have a plus and a minus. And then the factors of 3 are 1 and 3. So that even is relatively simple because I know I'm going to put a 1 in one spot and a 3 in one spot. I'm just not sure where yet, and I'm not sure which sign is going to go with which. So I have to watch out for both. Actually, let me fix this real quick before we get going too far. This is a plus 8 up here in the original problem. My apologies. So here's what ends up happening. I need the factors to subtract together to give me a positive 8. Well, if I put, because I only have 3 and 1, if I put 3 here and 1 here, regardless of what the sign is, when I do my outer, I get a 3x, and my inner, I would get a 3x. When I subtract those together, I'm going to get 0x. That's not going to work. So I need to switch those. I need to have the 1 in the first one, and I need to have the 3 out here. Now, my signs are opposite. See, I have a 9x and a 1x. So if I subtract those together, I will get 8x. But I need to have more positives than negatives because I need a positive 8x. So I'm going to put my plus out here with my 3 so that I have a positive 9x, and then I'll subtract my 1x from my inner, and that will give me that plus 8 in the middle. Now, both of these are factored, and when you factor trinomials, what our next step is really like when we did the factor tree and we looked for the common factors. Do our denominators already have any factors in common? Yeah, they both have an x plus 3. So when I'm thinking about my LCD, I know I'm going to have an x plus 3. That's what they have in common, so I only write it once. Then I write my other factors as well, just like I did with my factor tree. That first one has an x plus 2 as well, and my second one has a 3x minus 1. And again, Pearson is kind. They do not expect you to FOIL and FOIL that. Like, that's gross. And so they're letting you leave your denominators in the factored form, which is super nice. And so really what we're asking, if I need an x plus 3, an x plus 2, and a 3x minus 1, what is this first expression missing in the denominator? Yeah, that 3x minus 1. So that's what I'm multiplying the top and the bottom by, because that's the one term that's missing. And then I do the same thing over here on the right-hand expression. I have a 3x minus 1 and an x plus 3. So what am I missing? The x plus 2. So on top, I will do my distributing, but in the bottom, I get to leave it factored. I don't have to worry about that. So I'm going to distribute my 3 to my 3x, which gives me a 9x. 3 to the negative 1 gives me a minus 3. And then over here, I just have 1 times the x plus 2, so that makes my life pretty easy. And my denominator is the x plus 2 times the x plus 3 times the 3x minus 1. I don't have to worry about that. Leave it factored. Combine my like terms. I've got a 9x and a regular x, giving me a 10x. Minus 3 plus 2 gives me a minus 1. X plus 2, x plus 3, 3x minus 1. Nothing factors out of the 10x minus 1, so I know I'm good to stop there. questions, clarifications? All right, we got one more. Minus x over. So we're shifting back to binomials in our denominator a little bit, and that's okay. Because you can still factor binomials. We learned about how to pull out whatever they have in common. So if I'm looking at x squared minus 6x, is there anything I can pull out of that denominator? X. Because x times x minus 6 would give me the x squared minus 6. It's like the reverse of our distribution property. Then I'm going to do the same thing over here with my 6x minus 36. Does it have anything in common? The 6. And that will leave me with an x minus 6. So notice they already share something. They both have an x minus 6. So I know when I'm looking at my LCD, I'm going to have an x minus 6. And then I'm also going to multiply that by the parts that I didn't already box in. So I have an x and a 6. So I would take that times a 6x. So I'm just going to write the 6x first. Again, I'm not distributing it. I'm not doing any of that because they say I can leave it in factored form. I just like to write my binomial second. It looks a little nicer. So this one actually becomes pretty easy because what does the first expression need? Yeah, they need a 6. It's already got the x. It's already got the x minus 6. So the only piece it's missing is a 6. And my second one has the 6 and the x minus 6. So it's just mixing the x. 6 times 6 is 36. X times x is x squared. All over 6x times x minus 6. Do we notice anything at all about the top? It is a difference of squares. It's just kind of, like it looks a little bit backwards because usually we would have our x squared term first and then we'd have our number term second. But remember, whenever we want to change the signs on those, what do we do? If we want to reorder them and write it in the right way, I mean, we can switch it around and have a negative x squared plus 36, but then that doesn't look quite like difference of squares anymore. But if I wanted it to be a positive x squared and a negative 36, what could I do? Factor out that negative 1. And then difference of squares was one of our special factoring methods that we learned back from chapter 6. A difference of squares means that we will have, again, I'm going to leave the negative 1 out here, but the difference of squares gives me an x plus 6 times an x minus 6. So what do you notice now? The top and the bottom both have an x minus 6, which means we can cancel that out. They have something in common, so we can simplify it. Now at this point, the 6x and the x plus 6 and the negative 1, nothing else is going to cancel, so I'm going to go ahead and redistribute that negative just because I don't want to leave it in that factored form on top. Factored form on bottom is fine, but they always want you to have a simplified version on top. So give me a negative x minus 6 all over 6x. So sometimes there are cases where you will be able to cancel out factored forms. Looking at your homework, I want to say that only happens twice. I think it's number 9 and 10 in your homework on Pearson are the only ones where you will have something else factored that will eventually cancel. I know for a fact, because I also teach college algebra, this happens a lot in college algebra, especially when we're talking about our rational equations. And we have to be careful of these cancelings, because what ends up happening when we go to graph our rational equations is that those cancelizations will cause asymptotes and holes in our graphs. And if we don't cancel them, or if we cancel them incorrectly, then our graph ends up being messed up in the end. So you will continue to use this material later on in other courses as well as this